Hey guys, this is Cameron, and today we're going to be going over logistic growth, a Calculus BC topic. So we learned in Calculus AB that about population growth. And we learned that the differential equation to represent exponential growth was dp over dt is equal to some constant times the population. And the actual function was p of t equals the population times e to the power of some constant of proportionality times the time. This was an AB topic. It didn't consider death in a population, and it was exponential. And we knew to use it when we heard the phrase, the growth rate is proportional to the population itself. Today we're going to be talking about logistic growth, which is a little bit different. So logistic growth is represented by the differential equation dp over dt is equal to the same constant of proportionality times the population, also multiplied by 1 minus p over k. And this k representing the carrying capacity, which is now taken into account. What this basically means is as the population grows and get closer and closer to the carrying capacity, and eventually hitting the carrying capacity, it will no longer continue to grow. The function is p of t equals the carrying capacity over 1 plus this a value, which we'll get into later, times e to the power of the negative constant of proportionality times time. This is seen in nature like growth in bacteria instead of population, and death rate is accounted for. So, what do these variables mean? So this k value we've seen before, and it just represents the growth factor or the constant of proportionality. We know that this function represents the change in population with respect to time. This big P right here represents the population, and this big K right here represents the carrying capacity. The big K and the little k are different. To find this A value in the function, it is the carrying capacity minus the initial population over the initial population. 4 important limits to know in logistic growth is the limit st approaches infinity of p of t, which is k. The limit st approaches infinity of p prime of t, which is 0. The limit st approaches negative infinity of p of t, which is equal to 0. And the limit st approaches negative infinity of p prime of t, which is also equal to 0. We know that in a graph that represents logistic growth, p of t, as it goes to infinity, gets closer and closer to the carrying capacity. As it goes to negative infinity, it gets closer and closer to 0. And as you guys can see, the slopes are getting smaller and smaller each way, so those both approach 0. All right, so we're going to go through a couple practice problems from our worksheet. The first one being a logistic growth word problem, saying a desert ecosystem is able to sustain up to 100 rattlesnakes at a time due to limited resources. Initially, the desert contained 5 rattlesnakes, and after 2 days, there are 15. So we're going to use this information to basically respond to A, B, and C, and a calculator is allowed. So based on the information, we know that the initial population is 5 rattlesnakes, and after 2 days, there were 15 rattlesnakes. The carrying capacity, the K value, is 100 rattlesnakes based on the information that they gave us. And so after we write out our function p of t is equal to k over 1 plus a times e to the power of that negative constant of proportionality times time, we can put in the information that we know and solve for the unknowns. So once we plug in what we know, we get 100 over 1 plus 19 times e to the power of negative constant of proportionality times t. And so we're going to go through and solve for that k value. We're able to do this by using the information that we know that there are 15 rattlesnakes after 2 days. So we plug in 2 for the time, and we plug in 15 for the y value. Once we go through this algebraic work, you end up getting this ugly value for the constant of proportionality, which is this negative 1/2 times the natural log of 85 over 285. And once you plug this into your calculator, you get a nice 0.605. And then our final function we now have. So for part B, it says what is the value of k in the equation in the differential? So the small k in the differential is the same as the small k in the actual function. And we know that we found that value, which is 0.605. For part C, it says at what point will the graph of your equation have a point of inflection? So another way to say this is when will the population be growing the fastest? And this is when the carrying capacity is divided by 2, and that gives us our y value of 50. So now that we have the y value of when it's growing the fastest, we can now solve for when it's growing the fastest. So we do 50 equal to our function. Once we do that, and you go through the algebraic work of solving it, you end up getting a number of about 4.867, and that's the x value. and our x-coordinate would be 4.867, comma 50. All right, so with the next logistic problem we're going to go over is number 3, and it says interpret the function p of t is equal to 1,000 over 1 plus 9 times e to the power of negative 0.08 times t. So pt is equal to 1,000 over 1 plus 9 e 8t. So the first part asks us to find dp over dt, so we can actually just take advantage of structure here, because we know this is equal to small k times p times 1 minus p over k, and we can look at these values and adjust them to dp over dt. So now we can say dp over dt equals that 0.8 value is right here, 0.08 times the population times 1 minus p over 1,000, which is our carrying capacity. And there we have our dp over dt, or a differential problem. Now asking us for our carrying capacity. So our carrying capacity can be easily found by just looking at our function or by our differential equation, and that value is 1,000. So we want to make sure that we know both the structures of these functions so we can identify different parts. C asks us for our initial population. So our initial population actually can be easily found by just plugging in 0 for time. So p of 0 is 1,000 over 1 plus 9 e to the power of negative 0.08 times 0. So this is just p of 0 is equal to 1,000 over 1 plus 9 times e to the power of 0. So that's 1,000 over 10, which is 100. So our initial population is 100. Now they're asking us for when the population grows the fastest. So our population grows the fastest when our carrying capacity is divided by 2, and that gives us the y value of when we're going the fastest. But since they're asking us for the when, that's a x value, or a value of time. So we can plug in our y value, 500, equal to our function. Once we do that, we can solve algebraically, and we end up getting a time of about 27.465. So we can then state the population is growing the fastest at 27.465. So a point of inflection, so that's just another way of saying when is the population growing the fastest. And so we know that that's at 27.465, comma 500. So that is our point of inflection, or when our population is growing the fastest. So it's good to know because we need to be able to interpret both. So the 4 limits for logistic growth equations evaluated for p of t is what F asks us for. We know that the limit as t approaches infinity of p of t is equal to our carrying capacity of 1,000. The limit as t approaches negative infinity of p of t is 0. And the limit of p prime of t as it approaches infinity and negative infinity both equal 0. And this is clearly shown if we look at this graph right here when we interpret it conceptually.
This is Mira, and I'm going to be talking about Euler's method. So back in Calc AB, we learned how to do a linear approximation. You can see that the curve is in black, and then this line in red is the tangent line to the curve at the origin. And you could use this line in red to approximate points at any x value, like 1, 2, 3, so on and so forth, but its slope will always stay the same. However, in Euler's method, it's like a linear approximation, except we keep changing the slope of the tangent line so that it can stay with the curve. And you can see this is kind of the same shape as the curve. So how we do that is we start with the tangent line at the origin, but then when we get to 1, we plug the point 1, 2 into the equation for the derivative. We find the new derivative, which is less because the curve gets less and less steep. And then we do that again at 2, 3, 4, so on and so forth. And so this is what makes Euler's method a better approximation. And another thing to note is that the distance between the points where we change the slope of the tangent line, that's called the step size. And in this case, it's 1. Every 1, we're changing the slope, but it could also be 2, 1/2, 1/4, whatever you'd like. And the smaller the step size, the more accurate your Euler's method approximation will be. So now we're going to do the first problem in the Euler's method portion of our worksheet. And the problem says Ray had $20 in her savings account before she got an awesome job teaching calc. And after she gets the job, the amount of money in her savings account can be modeled by the quadratic equation f of x equals x squared plus 3x plus 20, where x represents the number of days that she's been working. So now we're going to approximate the amount of money in her savings account after 2 weeks by using Euler's method in 2 steps of equal size. So the first thing we want to do is figure out how big each step should be, and we want 2 steps of equal size. So 2 weeks is 14 days because the equation's in days, so we have to be careful. And then if we divide that by 2, we get that each step should be 7 days. So f prime of x, so the derivative of f of x is 2x plus 3, and I just did that with the power rule. And then, so the derivative at 0, I'm plugging in 0 into the equation 2x plus 3, and I got 3. So now what we're going to do is we're going to write an equation for the tangent line at x equals 0 using point slope form. So I have the slope here, and then x minus 0 plus 20, because that was the y value at 0. And now I'm going to plug 7 into that equation to get the y value approximation at 7. So f of 7 is 3 times 7 minus 0 plus 20, which is 41. Now we're going to repeat that process because our first step is done. Now we have to do the second step. So the derivative at 7 is 2 times 7 plus 3, again just plugging it into our first equation for the derivative, which is 14 plus 3, which is 17. So now we have our equation in point slope form, our second tangent line. So it's 17 times x minus 7 plus 41. And now we can plug in 14 to this equation to get the final approximation. So f of 14 is equal to 17 times 14 minus 7 plus 41. So 17 times 7 plus 41, which is equal to 160. So now that we have our approximation, we're going to plug in 14 into the actual equation, which, if you'll remember, was x squared plus 3x plus 20 to see how far away it was, to see the error. So I'm plugging in 14 here. I have 14 squared plus 3 times 14 plus 20, which is 196 plus 42 plus 20, which is equal to 258. And to get the error, it's really easy. All I have to do is subtract 160, which was our approximation, from 258, which was the actual value. And I got a difference of 98, which means that the error in our Euler's method approximation was $98. Okay, so now we're going to do the second problem on Euler's method on our worksheet. So the problem is actually a past AP test problem. So it says y equals f of x is a particular solution to the differential equation dy over dx equals 3x plus 2y plus 1 with the initial condition that f of 0 equals negative 2. So using Euler's method, we're going to start at x equals 0 with a step size of 1/2 to approximate f of 1. So the first thing we need to do is we need to calculate the derivative at the point 0, negative 2, which is our initial point, as the first part of our first step. So I'm just plugging it into that differential equation, so 3x plus 2y plus 1, and I got negative 3. So now I have my equation in point slope form, so it's negative 3 times x minus 0 minus 2. So now I'm going to plug in 1/2 to this equation. So f of 1/2 is negative 3 times 1/2 minus 0 minus 2. So that's f of 1/2 is equal to negative 3/2 minus 2, which is negative 7/2. So our first step is done. Now we're moving on to the second step. So we're going to take the derivative at 1/2, which we're going to plug in again to this equation. So it's 3 times 1/2 plus 2 times negative 7/2, which is the y value we got in the last step, plus 1, which is negative 9/2. Now we have f of x equals negative 9/2 times x minus 1/2 minus 7/2, our point slope form equation for the second step. And then because the final thing we want to approximate is f of 1, we're just going to plug 1 into there. So we have negative 9/2 times 1 minus 1/2 minus 7/2. So that's negative 9/2 times 1/2 minus 7/2, which is equal to negative 23/4. So that's our final answer for the approximation.